Right now, buried in NASA's planetary data archives, there may be images that could answer one of the most perplexing questions in modern astronomy. A billion-dollar space telescope recently stacked 9,000 images of an interstellar visitor and found something impossible, absolutely nothing where a comet's tail should be. Meanwhile, other instruments scream that gas is pouring off this object in torrents. The contradictions are so severe, so fundamentally irreconcilable, that some observations suggest we're not looking at a comet at all. The object is 3I Atlas only the third, confirmed interstellar visitor to our solar system, and it's behaving in ways that violate everything we thought we understood about these cosmic messengers. On October 14, 2025, astronomers released data that should have settled the debate. Instead, it deepened the mystery. Tonight, we follow the data trail through observation archives, missing spacecraft images, and experimental tests that could reveal whether 3I Atlas is the most unusual comet ever detected or something far stranger. We'll examine why different telescopes see completely different objects when they look at the same point in space. We'll explore the spacecraft that might hold the answers, but whose observations remain frustratingly out of reach. And we'll ask the uncomfortable questions that emerge when an object refuses to follow the rules. The stakes are higher than you might think, because if we can't explain this visitor with conventional physics, we'll need to consider possibilities that sound like science fiction. And the clock is ticking. Atlas is moving through our solar system right now, and every day that passes without decisive observations is a lost opportunity to understand what we're really looking at. So settle in, turn down the lights,
and let's begin our journey into one of the strangest cosmic mysteries of our time.
Imagine a night sky filled with telescopes, each one worth millions of dollars, all pointed at the same target. Hundreds of instruments from ground-based observatories to spacecraft floating in the silence of space, all tracking a single object as it races through our solar system. Now imagine that the most sensitive instrument of them all, after stacking over 9,000 individual images, says something nobody expected. It says there's no tail. The Transiting Exoplanet Survey Satellite. TESS is a spacecraft designed to find planets around other stars. It does this by staring at patches of sky for weeks at a time, watching for the tiny dips in starlight that occur when a planet passes in front of its host star. TESS is exquisitely sensitive to faint signals. It has to be. The brightness changes it's hunting for are often less than 1%, sometimes just a fraction of a percent. To find these subtle variations, TESS employs a technique that astronomers have used for decades: image stacking. Here's how it works. When you take a single photograph of the night sky, that image contains signal, the real light from stars and other objects, and noise, the random fluctuations from your detector. The background glow of the sky, cosmic rays hitting your sensor. If the object you're interested in is faint, the noise might overwhelm the signal, making it invisible. But if you take many images of the same field and add them together, something remarkable happens. The signal, which is always in the same place, adds up linearly. The noise, which is random, partially cancels itself out. With enough images, you can pull signals out of the darkness that would be completely invisible in any single frame. This technique, called co-adding, is like listening to a barely audible song and turning up the volume with each repetition until you can finally hear the lyrics. By October 2025, TESS had accumulated more than 9,000 frames of the region of sky containing 3 Atlas. When astronomers stacked these frames together, they expected to see structure. They expected to see the extended envelope of gas and dust that defines a comet, the luminous halo called the coma, and ideally the tail streaming away from the sun. What they found was a point source, a dot, nothing more. When you look at a star through a telescope, even the most powerful telescope humans have built, you don't see a disk, you see a point of light. This is because stars, despite being enormous, our sun is more than 1 million kilometers across, are so incredibly far away that their size collapses into a single pixel. Even the nearest stars just a few light years away appear as dimensionless points. The pattern of light you get from a point source is called the point spread function, or PSF. It's determined by the optics of your telescope, the diffraction of light as it passes through the aperture, and various instrumental effects. Every telescope has a characteristic PSF like a fingerprint. Comets are supposed to be different. A comet is not a distant, compact object like a star. It's a relatively nearby chunk of ice and rock that, when heated by the sun, releases gases and dust that spread out into space. This creates the coma, a diffuse cloud that can be hundreds of thousands of kilometers across, and often a tail that can stretch for millions of kilometers. When you image a comet, you should see this extended structure. The brightness shouldn't drop off sharply like a star's PSF. It should fade gradually as you move away from the nucleus, reflecting the distribution of dust and gas in three-dimensional space. TESS looked at 3i Atlas and measured its radial brightness profile, how the light intensity changes as you move away from the center. The profile dropped off exactly like a star, not like a comet. The analysis team could quantify this precisely. If there had been dust beyond a certain surface brightness threshold, they would have seen it. The stacking process increases the signal-to-noise ratio so dramatically that even extremely faint features become detectable. They could derive constraints on dust density, particle size distribution, and ejection velocity. All the numbers pointed to the same conclusion: whatever dust might be present around this object, it's not behaving the way comet dust should behave. It's not creating an extended coma visible to optical telescopes. It's not forming a tail that streams away from the sun under the pressure of solar radiation and the solar wind. But here's where things get strange. Other observations tell a completely different story. The James Webb Space Telescope, operating in the infrared, has detected water vapor and carbon dioxide around this object. Spectroscopic measurements techniques that split light into its component wavelengths like a prism show clear signatures of mass loss. Volatiles are escaping into space. These are the hallmarks of an active comet of ice sublimating and gases flowing outward. JWST's instruments can identify specific molecules by their unique spectral fingerprints, the precise wavelengths at which they absorb or emit light. The data is unambiguous. Gas is present, but where's the tail? Where's the visible evidence of all that material streaming away? You're forced into an uncomfortable corner here. Either the coma is so compact, so unnaturally dense and confined that it remains invisible to optical telescopes while still producing detectable gas signatures, or something else entirely is happening. It's like watching a campfire burn and seeing no smoke rise. You can feel the heat, you can smell the wood burning, but when you look up, there's no column of smoke. Either the smoke is being compressed into invisibility by some mechanism you don't understand, or what you're calling a fire isn't really a fire at all. The contradiction sits there, unavoidable. Tess spent months staring at this object with one of the most sensitive instruments we've ever built for detecting faint, extended structures. It saw nothing beyond a point source. But other instruments tuned to different wavelengths and different physical processes are screaming that something is definitely happening. Gas is flowing. Volatiles are escaping. Activity is occurring. One of these observations is missing something crucial, or our entire framework for understanding what a comet should look like is about to break. Here's what keeps astronomers awake at night. We've seen comets do strange things before, but we've never seen them do this. We've never had an object that so perfectly mimics a point source, while simultaneously showing chemical signatures of vigorous activity. The numbers don't just fail to add up, they actively contradict each other. This isn't a minor discrepancy that can be explained by different observing conditions or instrumental quirks. This is a fundamental disagreement about what the object is doing. The test data is public now. Anyone with the technical skills can download it, run their own analysis, check the numbers. The results are reproducible. The no-tail finding is solid, which means we need to figure out what's happening. Because if we can't explain this with conventional comet physics, we're going to have to start considering explanations that sound uncomfortably exotic. But before we get there, we need to understand just how deep these contradictions go and why different instruments are painting completely different pictures of the same object. Picture the James Webb Space Telescope swiveling its golden mirrors toward 3I Atlas. The observations come back crystal clear: carbon dioxide, water vapor, a gas coma rich in volatiles. The spectrographs are picking up molecular signatures, emission lines, showing atoms being excited, molecules vibrating, gases flowing outward from the nucleus. Spectroscopy is one of astronomy's most powerful tools. When light passes through gas, atoms and molecules absorb specific wavelengths, creating dark lines. When excited by heat or energy, they emit at those same wavelengths, creating bright emission lines. Each element has its own unique pattern, like a fingerprint. When JWST sees water vapor emission at 2.7 micrometers or carbon dioxide at 4.3 micrometers, there's no ambiguity. Those molecules are present, illuminated by sunlight, radiating into space. The JWST observations of 3I Atlas show exactly these signatures. Strong emission lines indicating substantial amounts of water and carbon dioxide in the immediate vicinity of the object. We can even estimate how much gas is being produced. The intensity of the emission lines, combined with models of how molecules emit at different temperatures and densities, allows us to calculate mass loss rates. The numbers suggest this object is venting volatiles at rates consistent with an active comet near perihelion, the closest point in its orbit to the Sun. SphereX. Another infrared mission has added its own observations to the mix. It reports large amounts of vaporized carbon dioxide around 3I Atlas, with carbon dioxide to water ratios that are unusual even by the standards of weird comets. Most comets in our solar system show water dominating their volatile emissions, with carbon dioxide as a secondary component. Some comets, particularly those from the outer reaches of the solar system, have higher CO2 ratios, but the proportions SphereX is seeing push into territory that's rare, though not impossible. So the infrared instruments, multiple independent instruments operating on different platforms, all agree this object is outgassing. It's releasing volatiles. It's active. It's doing what comets do. But here's the fundamental problem that no one has adequately explained. Ice doesn't sublimate without kicking up dust. Let me explain why this is so troubling. Comets are not made of pure ice. They're often described as dirty snowballs, though perhaps icy dirt balls is more accurate. The nucleus of a comet is a mixture of frozen volatiles, water, ice, carbon dioxide ice, carbon monoxide ice, and frozen organic compounds mixed together with rocky and metallic dust particles. When a comet approaches the Sun and its surface heats up, the ices begin to sublimate, transitioning directly from solid to gas without passing through a liquid phase. As this happens, the gas molecules don't just peacefully float away, they carry dust with them. Think of it like this. Imagine a block of ice with pebbles frozen inside it. As the ice melts or sublimates, the pebbles are released. They're dragged along by the flow of gas. In a comet, this process creates the dust coma and tail. The gas is invisible or nearly so in optical light, though it glows at specific wavelengths that infrared instruments can detect. The dust, however, scatters sunlight efficiently, and that's what creates the visible structures we associate with comets. The two processes, gas release and dust release, are physically coupled. You can't have large-scale gas sublimation without dust entrainment. The gas flow is violent at the molecular level, with velocities of hundreds of meters per second. Dust particles, unless they're extremely large or somehow chemically bound to the surface, get swept up in this flow. The ratio of dust to gas varies from comet to comet. Some are dusty, producing impressive tails. Others are gas-rich with less visible dust. But there's always some dust, always some visible signature of the activity that's occurring. except apparently with 3i Atlas. The infrared observations say massive gas production, volatile loss, active sublimation. The optical observations say no extended dust, point source appearance, no visible coma or tail. How do you reconcile these two statements? Let's consider the possibilities starting with the most conservative. Perhaps the dust is there, but it's the wrong size to scatter light efficiently at optical wavelengths. Dust scattering depends on the ratio between particle size and wavelength. Particles that are similar in size to the wavelength of light, around half a micrometer for visible light, scatter very efficiently. This is my scattering, and it's what makes dust clouds visible. But if the particles are much larger than the wavelength centimeters rather than micrometers, they don't scatter as well per unit mass. They're harder to see. They also have more inertia, making them harder to accelerate away from the nucleus. So one possibility is that 3i Atlas is producing dust, but the dust is predominantly large grains that hover close to the nucleus in a compact envelope. They don't scatter optical light efficiently, so they're faint or invisible to optical telescopes. But they still have ice on their surfaces, and that ice sublimates, producing the gas that infrared instruments detect. This would be unusual but not impossible. It would require a very specific size distribution with most of the dust mass in large particles, rather than the typical mix that includes plenty of small grains. Another possibility involves geometry and timing. Comets don't produce gas and dust uniformly in all directions. They have jets, localized sources where volatile rich material is exposed and actively sublimating. If 3i Atlas has jets that are pointed away from our line of sight, or if its activity is intermittent pulsing on and off, then we might catch it during quiet periods with optical telescopes, while infrared observations happen to occur during active phases. This could create an apparent contradiction where one instrument sees activity and another doesn't. But these explanations strain credibility when you look at the details. TESS observed continuously for extended periods. It should have caught any intermittent activity. The deep stacking should reveal even faint, compact dust structures if they're present. And while large grain dominance is possible, it's an ad hoc explanation invoked specifically to explain this one object rather than emerging naturally from our understanding of comet formation and evolution. There's another analogy worth considering. Imagine you're a detective arriving at a crime scene. You find blood evidence suggesting someone was injured. You find chemical traces indicating a violent struggle. But when you look for the victim, for the body, for physical evidence of violence, there's nothing. The room is pristine. How do you reconcile the chemical evidence with the lack of physical evidence? Either your chemical analysis is wrong, your search wasn't thorough enough, or something very unusual occurred that separated the chemical signatures from the physical aftermath. That's where we are with 3i Atlas. The chemical evidence says, comet activity. The physical evidence says, where's the comet? And the mystery is about to get worse, because when we look at how different telescopes see this object, we'll find that the contradictions aren't just between infrared and optical. They're everywhere. Different telescopes are telling fundamentally different stories about 3i Atlas. We're not talking about minor disagreements, we're talking about contradictions about what kind of object this is. JWST operates in the infrared observing wavelengths from 0.6 to 28 micrometers. At these wavelengths, it's not looking at reflected sunlight, but detecting thermal radiation and molecular emission. Molecules vibrate and rotate in quantized ways, emitting photons at specific wavelengths. JWST's spectrographs detect these emissions with extraordinary sensitivity. Critically, it doesn't need dust to detect a coma. It's listening directly to molecules singing their quantum songs. Ground-based optical telescopes work in visible light, 0.4 to 0.7 micrometers, looking at reflected sunlight. To see structure, you need extended dust particles spread out over space. If dust is too compact or particles are the wrong size, you might see nothing even if gas is pouring off the object. This is where scattering theory becomes crucial. The amount of light scattered by a particle depends on its size, composition, and shape. Small particles, micrometers in size, scatter visible light efficiently through scattering. They're what create the bright, diffuse coma and tails we associate with comets. Larger particles, millimeters to centimeters, have much lower scattering efficiency. They're darker, harder to see, and they stay closer to the nucleus because they have more mass and are harder to accelerate. If 3I Atlas is producing mostly large grains, optical telescopes would struggle to see an extended coma even if substantial dust mass is present. The dust would hover close to the nucleus in a compact, optically faint envelope. But that dust would still have ice on its surface, and that ice would sublimate, producing the gas that infrared instruments detect so clearly. Then there's geometry, the three-dimensional configuration of the sun, the object, and the observer. The phase angle, the angle between the sun, object, and Earth, dramatically affects what we see. When the phase angle is small, we're looking at the comet with the sun mostly behind us. This is forward scattering geometry, where light preferentially scatters back toward us, making dust structures brighter. When the phase angle is large, we're looking at the comet from the side or even somewhat from behind, and scattering is less efficient. Different instruments observed 3I Atlas at different times from different positions in their orbits, seeing the object from different angles. A tail that's visible from one viewing geometry might be foreshortened or hidden when seen from another. If we're looking almost directly along the tail axis, it appears much shorter or might be invisible entirely. It's the difference between looking at a broomstick from the side, where you see its full length, versus looking at it end-on, where it appears as a dot. We've seen cross-instrument disagreements before. Comet Ison in 2013 was predicted to be the comet of the century, and then disintegrated near perihelion, but different telescopes reported different levels of activity at different times, sparking debates about when it actually broke apart. Comet C 2017, K2, showed a coma in some observations and looked quiet in others, raising questions about whether it was truly active at its enormous distance from the sun or just venting gas intermittently. But the difference here is the scale of the disagreement. Atlas isn't just showing variations in brightness or activity level, it's showing a binary split, either tail or no tail, either point source or extended object. There's very little middle ground in the observations. The timing mismatches make the problem worse. JWST observed during specific windows determined by its observation schedule and the position of the object. Ground-based telescopes observed during others. TESS was staring continuously but at lower spatial resolution than dedicated pointing would provide. What if the object is intermittently active, pulsing out dust and gas in bursts rather than steady streams? Then one telescope might catch it during an active phase while another sees only quiescence. The observations would look contradictory even though both are accurately reporting what they saw at that moment. But even accounting for all these effects, scattering physics, viewing geometry, temporal variations, the level of disagreement is unusual. Deep stacking of optical images from professional observatories, the kind of analysis TESS performed, should recover faint dust features if they're there. The technique is tried and tested. It works. The fact that TESS, after stacking thousands of frames, sees nothing extended suggests that either the dust is extraordinarily compact, confined to a region smaller than TESS can resolve, or it's simply not there in the quantities we expect. And if it's not there, where's all that gas coming from? Gas doesn't just appear out of nowhere. It comes from ice sublimating off dust grains, or from the nucleus directly. Either process should produce dust as well. Ice isn't pure on comets. It's mixed with dust. You can't preferentially sublimate the ice and leave all the dust behind, not without some exotic mechanism that separates them. You start to wonder if you can trust any single instrument. Each one is seeing part of the elephant, reporting faithfully what its particular sensors detect. But the composite picture isn't coming together into anything coherent. It's as if you assembled a jigsaw puzzle and found that the pieces come from different puzzles entirely. This is where most astronomical mysteries get resolved. You gather more data, refine your models, realize you were missing some subtle effect like unexpected scattering properties or an unusual composition. Someone runs a simulation showing that yes, under these specific conditions, a comet could look point-like and optical while still producing detectable gas. Papers get published. The mystery dissolves into explained natural phenomenon, but every time we add another observation of 3I Atlas, the picture gets murkier instead of clearer. Each new data point raises more questions than it answers. And now we come to the spacecraft question, the observation that might actually resolve everything or make it infinitely worse. Because there's one instrument that might have had the perfect view, the perfect resolution, the perfect geometry to see what 3I Atlas really looks like up close. The Psyche mission was out there. Its trajectory might have brought it within viewing range. And if it captured images, where are they? Comets are ancient leftovers from solar system formation. Most originate in the Kuiper Belt beyond Neptune or the distant Oort cloud. When these icy bodies venture inward, sunlight warms their surfaces. Around 3 AU from the sun, water ice begins sublimating noticeably. The comet develops a coma that can grow enormous. As it approaches, closer activity intensifies. Gas and dust release increases. Solar radiation pressure and solar wind push this material away, creating tails stretching millions of kilometers. This behavior is predictable. We understand the physics. Sublimation rates depend on temperature, which depends on solar distance. We've sent spacecraft to comets. Rosetta spent 2 years with Comet 67P watching its evolution. The observations matched our models. Comets behave as expected. Now look at 3I Atlas. Vigorous gas production but minimal visible dust. Point source appearance after deep stacking designed to reveal faint structures. Unusual volatile ratios pushing boundaries of what we've seen. An object from another star system, but physics is universal. The statistical improbability is striking. Of thousands of observed comets, how many showed this combination, gas without optical tails? Point source despite confirmed activity. Contradictory observations across multiple independent instruments. The answer approaches zero. This is genuinely unprecedented. You might argue that 3I Atlas is just weird within the range of natural variation. Perhaps interstellar comets have different compositions. Perhaps the journey through the interstellar medium for millions of years alters surface properties in ways that change how comets behave when they enter a star system. Perhaps we're seeing the effects of cosmic ray exposure, interstellar dust impacts, or radiation processing that don't occur in comets that have stayed within the protective bubble of our heliosphere. These are reasonable hypotheses. They deserve investigation, but they need to explain specifics. Why would interstellar exposure preferentially affect dust production but not gas production? Why would cosmic rays alter surface structure in ways that confine dust but allow gas to escape freely? What physical mechanism could create that asymmetry? The scientific method confronts genuine anomalies through a process. First, you verify the observations. Are they real or are they instrumental artifacts? Processing errors or misinterpretations. For 3I Atlas, multiple independent instruments from different teams using different techniques all see the same contradictions. The observations are real. Second, you check your assumptions. Are you interpreting the data correctly? Could there be calibration issues, selection effects, or biases in how observations were made? The TESS analysis is rigorous. The JWST spectroscopy is solid. The ground-based observations come from experienced teams at professional facilities. The assumptions hold. Third, you try to fit the observations within existing frameworks. Can standard comet models, perhaps with unusual parameters, explain what you're seeing? This is where we struggle. Tweaking dust-to-gas ratios, adjusting particle size distributions, invoking special viewing geometries, none of it quite works. You're left with models that require very specific fine-tuned conditions that feel contrived rather than natural. Finally, when existing frameworks fail, you start considering alternatives. Not immediately jumping to exotic explanations, but methodically exploring possibilities that you previously hadn't needed to invoke. And that's where we are with 3i Atlas. At the threshold, looking at an object that refuses to fit the categories we've established over centuries of observation. An object that might be forcing us to expand those categories or perhaps create new ones. The history of astronomy is filled with moments like this.
Pulsars were discovered in 1967, and their regularity was so precise, their signals so unusual, that astronomers briefly considered whether they might be artificial beacons, hence the nickname LGM for Little Green Men, given to the first few discoveries. It turned out they were rotating neutron stars, a natural phenomenon, but one so extreme that it hadn't been predicted in detail before being observed. Fast radio bursts discovered in 2007 baffled astronomers for years. These millisecond flashes of radio energy, some coming from billions of light years away, had no obvious explanation. Hypotheses ranged from colliding neutron stars to evaporating black holes to, yes, artificial signals. Now we know they're likely produced by magnetars in distant galaxies, another natural but extreme phenomenon. The point is that the universe has a history of producing phenomena that initially seem impossible, that don't fit our models, that force us to reconsider what we think we know. Sometimes the answer is mundane, a mistake in the data, a misinterpretation. Sometimes it's exotic but natural, a new class of astrophysical object. And sometimes, very rarely, it's something that fundamentally changes our understanding. We don't yet know which category 3i Atlas falls into, but we're past the point where we can dismiss it as just a weird comet and move on. The anomalies are too severe. The contradictions are too sharp. The object is demanding an explanation, and we don't have a good one yet. But here's what we do have: observations that might exist but remain inaccessible. Spacecraft data that could resolve the mystery. Images that might show definitively what this object looks like. And that's where our investigation turns next, to the archives, to the spacecraft that might have seen what we need to see, and to the question of why that data isn't available.
The Psyche mission launched by NASA to study metallic asteroid 16, Psyche has been traveling through interplanetary space with imaging instruments. Its primary mission is reaching the asteroid in 2029, but during cruise phase, its cameras aren't dormant. They're regularly used for calibration navigation and opportunistic science. This is standard for interplanetary missions. You have sophisticated instruments traveling through space, passing near various objects. Mission planners take advantage pointing cameras at planets, moons, asteroids, testing systems, gathering bonus science, keeping instruments exercised. Based on publicly available ephemeris data, there are windows when 3i Atlas and Psyche had geometries where imaging would be possible. Whether Psyche's team actually commanded observations during these windows is information that would be in mission logs.
What would such observations show? Even from millions of kilometers, a spacecraft provides higher spatial resolution than Earth-based telescopes. Psyche might resolve structures at tens or hundreds of kilometers. On the object revealing shape, extended features, asymmetries. Most importantly, spacecraft images don't suffer atmospheric distortion. Ground telescopes peer through turbulent air that blurs everything. Even with adaptive optics, there are limitations. Space-based imaging sees with impossible from ground clarity. If Psyche captured Atlas images, they might definitively show whether extended coma exists, whether dust structures are present, whether the object is truly point-like, or shows spatial extent too faint for tests and ground telescopes to detect.
Those images might resolve the contradiction between infrared gas detections and optical point source appearance. The question is, where are those images NASA maintains archives of raw mission data? When spacecraft send back observations, that data gets stored in systems like the Planetary Data System, a comprehensive archive of solar system exploration data. The PDS is organized by mission and instrument with standardized formats that allow researchers to find and analyze observations from decades of planetary missions. Most space missions eventually release their raw frames, or at least metadata about what was captured and when. This is how discoveries happen years after original observations. Amateur astronomers have found comets and asteroids in old Hubble images. Researchers analyzing archival Cassini data from Saturn have discovered moon's rings and atmospheric phenomena that weren't noticed during the primary mission. The archives are vast, and no one can examine every frame of every observation systematically during mission operations. Later analysis, armed with better tools or looking for different things, reveals treasures. For Psyche specifically, the spacecraft generates images during cruise operations. Some of these have been released publicly. Calibration shots of Earth and the Moon from various distances, starfield images used for navigation verification. But there's been no public announcement of raw Psyche images showing 3I Atlas during any close approach periods. This absence could mean many things, and we need to be careful about jumping to conclusions. Let's walk through the benign explanations first, because they're perfectly plausible and don't require any conspiracy or cover-up. Spacecraft data, downlink, is a constrained resource. Deep space missions communicate with Earth using NASA's Deep Space Network, a collection of massive radio dishes in California, Spain, and Australia. But there aren't enough dishes to provide continuous coverage for all active missions. Each spacecraft gets allocated communication windows, time slots, during which it can transmit data back to Earth. During these windows, bandwidth is limited. A spacecraft can't send everything it records. Mission planners prioritize what gets transmitted. Engineering telemetry comes first, the health and status data that tells mission control whether the spacecraft is functioning properly. Then primary science data from the main mission objectives. Then secondary science extended mission observations bonus targets. Calibration frames and opportunistic observations are often lower priority. If Psyche's cameras captured images of Atlas, those frames might be sitting in the spacecraft's solid-state memory, scheduled for downlink during a future communication window when bandwidth becomes available. There's also data management to consider. Spacecraft don't have unlimited storage. They use ring buffers that cycle through recording new data and eventually overwriting old data when memory fills up. If Atlas images weren't flagged as high priority, if the science team didn't realize the object would turn out to be so unusual, those frames might have been assigned standard retention schedules. They might have been compressed to save space or, in worst case, overwritten by later observations considered more important at the time. This happens more often than the public realizes. Not every frame captured by a spacecraft makes it to Earth in full resolution, or even at all. Decisions about what to keep and what to discard are made by mission teams, working with limited resources, trying to balance science priorities, data volumes, and communication constraints. Then there are metadata and indexing errors. The images might exist in the archive but aren't properly cataloged. Wrong timestamps, mislabeled target fields, corrupted headers. Anyone who's worked with large astronomical databases knows how easily data can become effectively lost just by being filed in the wrong place or tagged with incorrect keywords. An image of Atlas might be sitting in an archive directory labeled as a calibration frame or a generic star field, waiting for someone to notice what's actually in it. Bureaucracy provides another explanation. Space agencies have embargo periods, data rights, policies, mission team, exclusive access windows. These policies protect the scientists who designed and built the instruments, giving them time to analyze and publish their findings before making data publicly available. It's common for mission data to remain proprietary for 6 months a year, sometimes longer. If Psyche captured Atlas observations, the science team might currently be analyzing them, preparing publications with public release scheduled for a date that hasn't arrived yet. All of these explanations are reasonable. They're based on how space missions actually operate, the real constraints that mission teams face, the normal friction of data handling in complex organizations. None of them require conspiracy or cover-up. They're just the reality of doing space science with limited resources. But here's the thing, absence of evidence is not evidence of absence. We don't know what was captured because we can't see the full archive. We don't know what was prioritized for downlink, what was compressed, what was labeled how. The metadata that would tell us might itself be incomplete or inaccessible. What we can do, what should be done, is ask. Freedom of information. ACT requests can compel release of government-held data, though the process can take months, and responses can be heavily redacted or claim exemptions. Mission logs, observation schedules, instrument activity reports. These are documents that exist and can in principle be requested. The question is whether the images that might resolve the Atlas mystery are sitting in an archive somewhere waiting to be discovered, whether they were never captured or whether they exist but are being held for reasons we don't yet understand. This is where the story could go in multiple directions. If the images exist and get released, we might finally see what 3i Atlas really looks like, resolving the contradictions between TESS and JWST and everything else. If they don't exist, we need to figure out why a spacecraft with working cameras didn't capture what might be the astronomical event of the decade. And if they exist but can't be accessed, then we have a different kind of problem entirely, one that raises questions about transparency and data governance in space science. The investigation requires patience and persistence, but it's not impossible. The tools exist. The procedures exist. What's needed is the determination to navigate bureaucracy, file the requests, search the archives, and keep pushing until we get answers. Or at least understand why answers aren't available. Because somewhere in server farms and data archives, the truth about 3i Atlas might already exist, stored as strings of ones and zeros waiting to be retrieved. Let's follow a single photon's journey from 3i Atlas as it becomes archived data or doesn't. The photon strikes Psyche's camera sensor, which converts light into electrical signals. These get digitized into numbers representing pixel brightness. This happens millions of times per second, creating a digital image. Already, information is lost. Analog to digital conversion has finite precision. Electronic noise adds uncertainty. Cosmic rays constantly strike the detector, creating bright streaks that look like stars, but are artifacts requiring removal. The raw image enters spacecraft memory. It might be compressed immediately. Lossless compression preserves everything but achieves modest reduction, while lossy compression throws away information for greater size savings. The choice affects what science can be extracted later. The image sits in memory with thousands of other frames, telemetry, and instrument data. The spacecraft has downlink schedules, communication windows lasting hours every few days. But bandwidth is limited. A single high-resolution image might take hours to transmit across millions of kilometers. Mission controllers prioritize. Critical engineering data first, then primary science, then everything else by scientific priority. If Atlas observations were low priority, just bonus science, they wait in queue while other data transmits first. The spacecraft uses ring buffers for non-critical data, continually overwriting oldest data unless flagged for preservation. If Atlas images weren't flagged, they might have retention times of days or weeks before automatic deletion. Eventually, hopefully, the data gets transmitted to Earth and arrives at mission operations. Now it enters the ground data processing pipeline. The raw frames need to be converted from spacecraft format into standard scientific formats. Headers must be populated with metadata observation time target coordinates, exposure duration filter settings, instrument temperature spacecraft pointing quality flags. This metadata is crucial because it's how anyone searches the archive later. But metadata entry is tedious and error-prone. It's often done through automated scripts that extract information from telemetry and populate database fields. If the scripts have bugs, if timestamps are offset, if coordinate transformations are computed incorrectly, data gets mislabeled. An image of Atlas might be filed with wrong coordinates or a wrong timestamp, making it effectively invisible to anyone searching for Atlas observations. The data then moves into the archive system, typically the Planetary Data System for NASA missions. The PDS has strict formatting requirements and organizational hierarchies. Data is organized by mission, then instrument, then observation date, then target. Finding something requires knowing where to look, which hierarchies to navigate, which directory structures to descend through. Archives get reorganized, migrated to new storage systems, re-indexed as software evolves. Each migration is an opportunity for errors. File corruption can occur. Checksums cryptographic hashes that verify file integrity can mismatch if data degrades. Links between data files and their metadata can break if directory structures change, but database pointers don't get updated. Large archives with millions of files are almost guaranteed to have some fraction that are damaged, mislabeled, or inaccessible due to technical glitches. It's not malice, it's entropy. It's the inevitable degradation that affects all complex systems over time. Then there are embargo periods and proprietary data rights. Mission teams often get exclusive access to their data for months or years before public release. This policy exists to protect the scientists who spent years or decades designing instruments, proposing missions, and fighting for funding. They deserve first crack at analyzing their data and publishing results before the broader community gets access. But embargo periods can stretch. If a mission team is understaffed, if analysis takes longer than expected, if team members get pulled onto other projects, data release gets delayed. The data exists, but it's in a restricted archive accessible only to team members. An outsider requesting access gets told to wait for the official release date, which might be months or years away. Bureaucratic delays compound the problem. Releasing data requires resources. Someone must prepare files, write documentation, verify quality setup access systems. At space agencies and observatories that are chronically understaffed and overworked, data release tasks compete with mission operations, instrument maintenance, and new proposal preparations. Low-priority data release tasks get pushed to the bottom of the queue. Historical examples show that important data can be recovered from archives years after collection. Reanalysis of Hubble archival images has discovered gravitational lenses, distant galaxies, and variable stars that weren't noticed in original processing. Voyager tapes were found in storage decades later, preserving observations that had been thought lost when original magnetic tapes degraded. Amateur astronomers have found comets and asteroids in publicly released images that professionals overlooked because they were focusing on different science targets. This structural blindness affects all of astronomy, not just 3i Atlas. We're only seeing the subset of the universe that gets observed successfully, downlinked, properly archived, and labeled and analyzed by someone with the interest and resources. The true universe is filtered through this entire pipeline, and we don't know what we're missing. For Atlas specifically, this means several things. First, the contradictions between instruments might partially reflect pipeline effects rather than genuine physical differences. TESS sees no extended coma, partly because its data processing is optimized for stellar photometry, for finding planets, not for detecting faint extended sources around comets. Ground telescopes might miss faint tails because their reduction pipelines assume point sources and don't apply the specific techniques needed to bring out low-surface brightness structures. Second, the absence of Psyche images in public archives could be explained by any of dozens of pipeline failures or delays, none requiring conspiracy. But explaining the absence doesn't make it less frustrating. If observations exist, scientific integrity demands they be accessible for analysis. If they don't exist, we should know why observation opportunities were missed. Third, this suggests a research strategy. Don't just look at published results or official releases. Dig into archives directly. Download raw frames if available and reprocess them with different assumptions. Look for metadata inconsistencies that might indicate mislabeled observations. Check observation logs against actual archive data to find discrepancies. File access requests to push institutions toward greater openness.
Citizen science has a role here. Amateur astronomers and data scientists who aren't constrained by institutional pressures or career concerns can ask uncomfortable questions and pursue analyses that professionals might avoid. They can collaborate across communities, sharing data and methods, building tools that make archives more searchable and accessible. The structural blindness is real, but it's not insurmountable. It requires persistence, technical skill, and willingness to navigate bureaucracy. It requires building coalitions of people who care enough about getting answers to do the unglamorous work of data archaeology. And it requires maintaining pressure on institutions to improve their data pipelines, their release schedules, their transparency, because ultimately the data exists. Photons hit detectors. Signals were recorded. Bits are stored somewhere on hard drives or tape archives or solid-state memory.
The question is whether we can access them, verify them, and analyze them openly. That's a question of policy and priority as much as physics. And it's the question we need to answer if we're going to understand what 3I Atlas really is. Let's step back and do what scientists are supposed to do. Generate hypotheses, make predictions, and figure out what observations would support or refute each one. We'll start with the most conservative explanations, the ones that keep 3I Atlas within the realm of unusual but still natural cometary phenomena. These models represent about 60% of the probability space, not because we're certain they're right, but because they require the fewest assumptions beyond what we already know about comet physics. Model 1 large, inert body with micro-outgassing. Imagine a chunk of rock and ice from another star system mostly inert, but releasing small gas amounts through cracks or rare volatile-rich pockets. This explains gas signatures without massive dust production. If only a small surface fraction is active, if gas escapes through localized vents, you might get substantial emission without much dust. The problem is quantifying production rates. JWST's measurements suggest significant volatile loss. You can't hide that much in microcracks without implausibly high outflow velocities. And even micro-outgassing should entrain some visible dust. Model 2 fragment cloud or rubble swarm. What if 3I Atlas isn't one object but a tightly bound swarm of smaller fragments traveling together individually, unresolvable but collectively producing measured brightness? Each fragment produces gas and dust, but material stays confined within the swarm. Collective surface area might explain high gas production, while dust remains trapped through collisions or electrostatic effects. This could explain point-like appearance if fragments cluster within regions smaller than our resolution, but why would fragments stay bound over interstellar distances? The journey takes millions of years. You'd need surprisingly strong cohesion or recent breakup during solar approach.
Model 3, unusual dust. With large grain dominance. Maybe 3I Atlas produces dust, but it doesn't scatter light as expected because particle properties are unusual. If the size distribution strongly favors large grains, millimeter or centimeter particles, they wouldn't scatter visible light efficiently. They'd be dark, faint, hard to see. but ice mantles on surfaces could still sublimate, producing detectable gas. Large particles would also have more inertia, hovering near the nucleus in compact envelopes rather than accelerating into extended tails. The challenge is explaining why Atlas would have such unusual size distribution when normal comets show ranges from submicron to centimeter sizes. Each of these natural models requires special pleading, invoking specific conditions or unusual properties to explain the observations. None fits perfectly.
But they're all within the realm of known physics, and given how little we know about interstellar objects, we've only seen 3 of them up close. It's entirely possible that interstellar comets simply behave differently than solar system comets in ways we're only beginning to discover. The way to test these models is through specific predictions. The micro-outgassing hypothesis predicts we should eventually detect faint dust if we stack enough observations or catch the object during an active phase. The fragment swarm model predicts structural variations over time as the swarm evolves and spreads. The large grain model predicts specific polarization signatures and thermal emission patterns. Get those observations, make those measurements, and we'll start narrowing down which natural explanation, if any, fits the data. These are testable, falsifiable hypotheses. That's how science progresses, not through wild speculation, but through careful model building and systematic testing. But there are other models to consider, ones that push into more exotic territory while still remaining natural. Let's explore those next. Now we venture into territory that's less comfortable, explanations that invoke physics we know is real, but haven't observed operating at these scales or in these contexts before. This is speculation, but it's grounded speculation based on established science rather than pure imagination. These models represent perhaps 25% of the probability space possible, but requiring conditions or mechanisms we haven't confirmed. Here's something we know is true: dust particles in space can become electrically charged. Ultraviolet light from the sun knocks electrons off particle surfaces through the photoelectric effect, leaving the particles positively charged. Electrons from the solar wind or planetary magnetospheres can accumulate on particles, charging them negatively. The balance between these processes determines the particle's final charge, and it depends on particle composition, solar wind conditions, and proximity to magnetic fields. We've seen charged dust create spectacular effects. In Saturn's rings, tiny particles levitate above the ring plane, suspended by electromagnetic forces. Dust grains in planetary ring systems show organized behavior, responding to magnetic fields and plasma conditions. On the Moon, where there's no atmosphere to dampen effects, electrostatically charged dust can actually hop across the surface during sunrise and sunset, when changing illumination creates steep electric field gradients. So the question isn't whether charged dust exists, it definitely does. The question is whether electromagnetic forces could be strong enough around 3I Atlas to confine dust close to the nucleus, preventing it from escaping into a visible tail. For this to work, you'd need several things. First, the nucleus itself would need to develop a substantial electric charge or magnetic field. How might this happen? One possibility involves the object's interaction with the solar wind. When solar wind plasma, a stream of charged particles constantly flowing outward from the sun, encounters an object with an ionized atmosphere complex, electromagnetic interactions occur. The solar wind drapes around the obstacle, creating an induced magnetosphere. Comets do have induced magnetospheres, but they're typically weak, not strong enough to trap dust particles. For electromagnetic confinement to be effective, you'd need fields perhaps 10 to 100 times stronger than what typical comets produce. Where would that enhanced field come from? One speculative possibility: if 3I Atlas has a partially metallic or conductive core, if its interior contains more metal than typical comets, then interactions with the solar wind might generate stronger induced fields.
We know that some asteroids are thought to be fragments of differentiated protoplanets with metallic cores exposed. Could an interstellar visitor have similar properties? Another possibility involves the object's rotation. If it's spinning and has internal charge separation conductive materials in the interior, insulating materials at the surface, it might act like a dynamo generating its own magnetic field. This is how Earth's magnetic field works. Through convection of conductive material in the outer core. Obviously, a comet nucleus is vastly smaller and colder than Earth's interior, so the mechanism would be different, but the principal moving charges generating magnetic fields is universal. If you had strong enough fields, dust particles released from the surface could be trapped. Positively charged particles might be confined by electric fields circulating in the coma rather than escaping. The dust would still be there, still present, but held close to the nucleus in a compact envelope rather than streaming away. The gas, being electrically neutral or only weakly ionized, would escape normally, explaining why JWST sees gas signatures, but optical telescopes see no extended dust structure. This model makes specific testable predictions. If electromagnetic effects are important, we should see polarization anomalies. Light scattered by dust in magnetic fields shows characteristic polarization patterns that differ from simple dust scattering. Detailed polarimetry might reveal these signatures. Radio emission charged particles accelerating in magnetic fields produce synchrotron radiation at radio frequencies. If 3I Atlas has organized fields and trapped charged particles, radio telescopes might detect faint emission. Faraday rotation radio waves passing through magnetized plasma have their polarization angle rotated. If background radio sources are viewed through Atlas's coma, their polarization should show rotation proportional to the field strength. X-ray emission beyond normal charge exchange. While comets do produce faint X-rays through charge exchange between solar wind ions and neutral atoms in the coma, stronger magnetic fields might accelerate particles to higher energies, producing enhanced X-ray emission. The challenge is that we haven't made these observations yet, or if we have, they haven't been published. Without direct evidence of enhanced electromagnetic activity, the model remains speculative. But it's not wild speculation, it's based on known physics, just operating at scales or in combinations we haven't previously encountered. Related to the electromagnetic hypothesis is the idea that 3I Atlas might be surrounded by a denser than normal plasma environment that affects how dust behaves. Plasma ionized gas, where electrons have been separated from atoms, is often called the fourth state of matter. It doesn't behave like a gas in our everyday experience. It responds to electromagnetic forces, can support waves and instabilities, and has collective behaviors that emerge from the interactions of vast numbers of charged particles. In space, plasma is everywhere. The solar wind is a plasma. Earth's magnetosphere contains plasma. The region around an active comet nucleus, where solar ultraviolet light ionizes gas, creates a plasma coma within the neutral coma. What if 3I Atlas, for reasons related to its composition or the conditions it encountered during its interstellar journey, develops an unusually dense plasma coma? This could happen if it has higher than normal volatile content, rich in easily ionized species. Carbon dioxide, for instance, ionizes more readily than water under solar UV irradiation. A dense plasma coma would interact strongly with dust particles through Coulomb forces, the electric attraction and repulsion between charged particles. In some conditions, this interaction can create collective effects, where dust particles of similar charge repel each other but are collectively confined by the background plasma's electric fields. It's similar to how individual electrons in a metal repel each other, but are collectively bound by attraction to the positive ion lattice. This model could explain a compact dust distribution without invoking permanent magnetic fields. The confinement is dynamic, maintained by the ongoing interaction between dust plasma and solar radiation.
Turn off the solar illumination and the effect disappears. Predictions. Dense plasma should produce detectable radio emission from plasma oscillations, specific spectral lines from ionized species, and perhaps even plasma waves that could be detected if any spacecraft passed nearby. Here's a different kind of exotic natural explanation. What if the ice on 3I Atlas is in a crystalline rather than amorphous form? This matters because crystalline ice and amorphous ice have different properties. Amorphous ice is disordered at the molecular level like glass. It forms when water vapor deposits directly onto cold surfaces in space. Crystalline ice has organized molecular structure like snowflakes.
It forms when amorphous ice is warmed above about 120 Kelvin, or when water freezes slowly from the liquid state. Most comets are thought to contain primarily amorphous ice because they formed in the cold outer regions of the solar nebula, where temperatures never rose high enough for crystallization. But an interstellar visitor might have a different history. If it formed in a warmer disk around another star, if it experienced heating events during its interstellar journey, or if it spent time in an environment where cosmic rays or radioactive decay provided steady, low-level heating, its ice might have crystallized. Crystalline ice releases trapped gases differently than amorphous ice. When amorphous ice is heated and transitions to crystalline structure, it can release a burst of volatiles that were trapped in the disordered structure. Crystalline ice also sublimates at slightly different rates and might incorporate dust differently into its structure. Could this explain Atlas's behavior? Perhaps, though, it requires a fairly specific scenario. The model would predict that gas release might be enhanced during certain temperature ranges, corresponding to crystallization transitions, that isotopic ratios might show signatures of heating history, and that the coma composition might reveal whether ice underwent phase transitions. None of these exotic natural models is fully satisfying. Each explains some observations while creating questions about others. Each requires invoking conditions or mechanisms that, while not impossible, push beyond the typical comet paradigm, but that might be appropriate. 3I Atlas isn't a typical comet. It's an interstellar visitor formed in a different stellar system subjected to millions of years of cosmic ray exposure and interstellar medium interactions, arriving in our solar system with a history we can't fully reconstruct. Perhaps we should expect it to behave unusually. The key is testing. Make predictions, perform observations, see which models survive. Contact with data. Science doesn't progress through pure speculation. It advances through the cycle of hypothesis, prediction, observation, and revision. Still, there's one more category of explanation. We need to consider the one that makes scientists most uncomfortable, but that we cannot dismiss without evidence. What if 3I Atlas isn't natural at all? This is speculation. I need to be completely clear about that. Nothing discussed here is proven or even strongly suggested by current data. But given the anomaly's severity, we have an obligation to consider uncomfortable possibilities. This represents perhaps 15% of the probability space. The question, what if 3I Atlas's artificial scientists are reluctant to consider this for good reasons? Extraordinary claims require extraordinary evidence, and detecting alien technology is extraordinarily extraordinary. History shows false positives pulsars, initially designated LGM before recognition as neutron stars, the unexplained wow signal. Tabby's stars' dimming patterns, initially suggesting megastructures before dust clouds seemed likely. The lesson, when you encounter strangeness when observations don't fit the answer, is almost always natural but unusual. Almost always, but not always. What would an artificial object need to do to produce our observations? First, mimic the brightness and appearance of small solar system bodies. Trivial for anything with reflective surfaces, spacecraft with metallic hulls, or solar panels would reflect sunlight as asteroids do. Second, produce gas signatures, JWST detects. More challenging, but possible. If the object carries propellant water ice, carbon dioxide volatiles for thermal management routine, venting would produce exactly the spectral signatures we see.
Spacecraft operating far from the sun need thermal control managing heat through venting volatiles. The troubling aspect this hypothesis explains the central mystery perfectly. Artificial objects wouldn't produce dust tails. They'd vent gases for propulsion attitude control or thermal management without releasing dust unless components degraded. The compact appearance point source signature TESS-Cs would be natural for manufactured objects. Gas release would be controlled, deliberate, potentially intermittent. Third, it would need to survive the interstellar journey. This is actually less of a problem than you might think. The space between stars is nearly perfect vacuum close to absolute zero temperature with minimal hazards beyond cosmic rays and the occasional dust grain. A well-designed spacecraft could last for millions of years in those conditions, possibly longer. It's not like crossing an ocean where salt water corrodes and organisms attach themselves to hulls. Space is extraordinarily benign for long-term material preservation. Now, why would another civilization send probes to other star systems? We're planning to do this ourselves. The Breakthrough Starshot initiative proposes sending gram-scale probes to Alpha Centauri using laser-pushed light sails. These probes would make the journey in decades, accelerated to 20% of light speed, far beyond anything we could achieve with chemical rockets or even nuclear propulsion. If we're contemplating interstellar missions with current or near-future technology, it's reasonable to assume that other civilizations, if they exist and achieve spaceflight, might do the same. They might send probes to explore nearby star systems, to study potentially habitable worlds, to establish communication relays, or for reasons we can't anticipate, because their motivations and goals might be fundamentally different from ours. The timing of 3I Atlas's arrival in an era when humanity has developed telescopes capable of detecting and characterizing interstellar visitors is interesting, but not necessarily meaningful. We've only had the capability to detect such objects for the last couple decades. Before wide-field digital surveys, an interstellar visitor could have passed through the inner solar system undetected. We might have seen it only if it happened to become a bright, naked-eye comet, and even then we wouldn't have recognized it as interstellar without orbital calculations. So, the fact that we're detecting these objects now might simply be selection bias. We're finally capable of seeing them, so we're seeing them. If interstellar probes are common, if dozens or hundreds pass through our solar system every century, we'd only start noticing them in the era of automated sky surveys like Pan-STARRS, which discovered the first confirmed interstellar visitor, 1I Oumuamua, in 2017. The artificial hypothesis makes specific testable predictions that differ from natural scenarios. Geometric structure. Natural bodies are lumpy, irregular, shaped by accretion collisions and gravitational forces. While they can be elongated or have unusual shapes, they don't show geometric precision. An artificial object might have smooth surfaces, right angles, symmetric features, or articulated components. High-resolution imaging would reveal this. Spectral anomalies. Natural comets produce a predictable suite of molecules from the sublimation of primordial ices. An artificial object might show spectral lines from industrial materials, unusual metal oxides, synthetic polymers, or isotope ratios that don't occur naturally. Technetium, which only exists as a product of nuclear reactions, would be a smoking gun. So would complex organic molecules that are easier to synthesize than to form naturally. Temporal patterns, suggesting control. Natural activity is chaotic or follows simple periodic patterns based on rotation and solar heating. Artificial activity might show complex patterns, correlations between different observables, or behavior that adjusts in response to environmental conditions in ways that suggest intentionality rather than passive response. Multi-wavelength signatures. If the object has power systems, electronics, or active propulsion, it might emit at wavelengths and in patterns inconsistent with thermal radiation or natural processes. Radio emission at specific frequencies, X-rays from energy conversion systems, or modulated signals would all suggest technology. The burden of proof for claiming artifact status is appropriately high. You'd need multiple independent lines of evidence data whose provenance is unquestionable observations that rule out natural explanations through a systematic process of elimination, and ideally some signature that's definitively technological rather than just unusual. We don't have that evidence yet. What we have are anomalies, contradictions, observations that don't fit standard models. These anomalies warrant serious investigation, but they're not proof of anything artificial. The reason to discuss this hypothesis at all, despite the stigma, despite the risk of being labeled a sensationalist or a conspiracy theorist, is that dismissing possibilities without investigation is antithetical to science. If we rule out the artificial explanation solely because it makes us uncomfortable, solely because the social and professional costs of being wrong are high, then we're letting non-scientific factors drive our reasoning. The proper approach is to investigate, rigorously test hypotheses systematically, and follow the evidence wherever it leads. If that evidence ultimately shows 3I Atlas is a weird comet with unusual but natural properties, excellent. We've learned something new about the diversity of objects the universe produces. If the evidence points towards something else, something that doesn't fit natural categories, then we need the intellectual courage to accept that conclusion and its implications. The universe has already shown us it can produce phenomena we didn't predict. Black holes seemed like mathematical curiosities until we found them everywhere. Gravitational waves were debated for decades before LIGO detected them. Exoplanets were speculative until we discovered thousands. Dark matter and dark energy make up 95% of the universe's energy budget, and we still don't know what they are. Given all that, given how often the universe has surprised us, is it really so implausible that we might encounter technology from another civilization if intelligent life exists elsewhere and the sheer size and age of the universe suggest it might? Then their technology could be traveling through the galaxy just as we're beginning to send probes beyond our solar system. The question isn't whether we should consider this possibility. It's whether we have the tools, the data, and the will to investigate it properly. And that brings us to another strange object that's forcing astronomers to question their models, a phenomenon in our own galaxy that might connect to our investigation of 3I Atlas in unexpected ways. Using the Australian Square Kilometre Array Pathfinder and NASA's Chandra X-ray Observatory astronomers discovered an object that pulses every 44 minutes. Not approximately 44 minutes, exactly 44:07 minutes, repeating with clockwork precision. The object emits a 2-minute radio burst, goes silent for 42 minutes, then bursts again. Endlessly. That's already strange. Long-period transients objects flashing every tens of minutes to hours are relatively new. We've only discovered them recently because we didn't have radio telescopes continuously monitoring sky with sufficient sensitivity. They're rare, poorly understood, don't fit existing classifications. But ASCAP J1932 is stranger still. It's the first long-period transient pulsing, not just in radio but also X-rays simultaneously. Chandra shows X-ray pulses synchronized with radio bursts, not perfectly overlapping but definitely correlated. The object is doing something at 44-minute intervals, producing high-energy radiation across multiple wavelengths. What could this be? Immediate suspects are magnetically active objects. Magnetars neutron stars with insanely powerful magnetic fields pulse. But magnetar pulses are milliseconds to seconds, not 44 minutes. You'd need some novel configuration, some reason for fields to store energy slowly and release periodically. Nobody has a convincing model.
White dwarfs are another possibility. But again, the 44-minute period is unusually long. Binary systems might work if two objects orbit with that period, but that implies they're extremely close, should have merged, or be spiraling in rapidly. Every model requires special pleading, unusual conditions. None are satisfying. And this is relevant to 3i Atlas because it demonstrates something crucial. The universe contains phenomena we don't fully understand. Our catalog of known objects isn't complete. When we encounter something that breaks our models, that doesn't fit existing categories, we shouldn't immediately dismiss it or force-fit it into inappropriate boxes. We should recognize that we might be looking at something new. ASCAP J1832 is proof that natural processes can produce behaviors we haven't predicted, that our theories, even well-tested theories, have gaps. If one object in our galaxy can generate a 44-minute pulse pattern that doesn't match any known class of star, neutron star, black hole, or binary system, then we should be humble about declaring what is and isn't possible for other weird objects we encounter. The discovery also highlights observational bias. ASCAP is a relatively new radio telescope array only operational for a few years. Chandra has been operating since 1999, but it can only observe what we point it toward. ASCAP J1832 has probably been pulsing for thousands or millions of years. We only just noticed because we finally built instruments capable of detecting it and pointed them at the right patch of sky. How many other strange objects are out there detectable with current technology but not yet found? How many anomalies are lurking in the data, waiting for someone to look in the right way or ask the right question? This is the context in which we should evaluate 3i Atlas. Before ASCAP J1832 was discovered, you might have confidently stated that natural objects don't produce periodic radio and X-ray pulses every 44 minutes. You'd have been wrong, not because of faulty logic, but because your catalog of known phenomena was incomplete. Similarly, before 3i Atlas, you might have confidently stated that objects showing vigorous gas production must also show visible dust tails. That contradictory observations across multiple wavelengths always resolve into consistent pictures when you account for instrumental effects. That interstellar visitors, while interesting, fundamentally behave like solar system comets once you account for compositional differences. Maybe those statements are wrong too. Maybe we're discovering that our models need expansion, that the universe's playbook includes scenarios we haven't imagined. Maybe 3i Atlas and ASCAP J1832 are both entries in a catalog of cosmic weirdness that's only beginning to be written. Or maybe, and this is pure speculation, a thought experiment rather than a claim, maybe they're related in ways we haven't considered. Not through shared identity. They're clearly different types of objects in different contexts, but perhaps through shared physics, through electromagnetic or plasma processes that can operate at vastly different scales and produce qualitatively similar anomalies. This is the frontier of astronomy, not the confirmation of what we already know, but the exploration of what we don't. And right now, we don't know what 3i Atlas is. We don't know what ASCAP J1832 is, but we have the tools to find out if we're willing to look. On an otherwise unremarkable day deep beneath the Mediterranean Sea, a neutrino crashed into the detection array known as KM3net and shattered every expectation about what should be possible. The neutrino carried 220 peta-electron volts of energy. To put that in perspective, it's 16,000 times more energetic than protons accelerated by the Large Hadron Collider, the most powerful particle accelerator humans have ever built. Let me explain why this matters. Because the connection to 3i Atlas might seem obscure at first, but it's more relevant than you'd think. Neutrinos are ghost particles. They're fundamental particles with almost no mass and no electric charge, which means they interact with normal matter incredibly weakly. Right now, as you listen to this, billions of neutrinos from the sun are passing through your body, through the Earth, continuing into space without interacting with a single atom.
They're everywhere, produced copiously in nuclear reactions, but they're nearly impossible to detect because they don't bump into anything. To catch a neutrino, you need an enormous volume of transparent material water or ice, instrumented with sensitive light detectors, watching for the extremely rare occasions when a neutrino does interact. When a high-energy neutrino collides with an atomic nucleus, it can produce a muon or other charged particle. That charged particle travels through the water or ice faster than light travels in that medium, creating a characteristic cone of light called Cherenkov radiation. That's what the detectors see, a flash of blue light lasting nanoseconds containing directional information about where the neutrino came from. KM3net operates in the Mediterranean using the sea itself as the detector volume, with arrays of sensors monitoring cubic kilometers of water. The ARSER component specifically designed for neutrino astronomy detected this 220 PeV event and analyzed its properties. The energy calculation is solid. This isn't a glitch or misidentification. It's real. Why does this matter? Because neutrinos at these energies point to cosmic accelerators operating at scales we barely understand. The most powerful candidates are blazars, supermassive black holes, at the centers of distant galaxies that are actively feeding. These black holes launch jets of plasma at nearly the speed of light. Those jets can accelerate protons to enormous energies. When those ultra-high energy protons collide with ambient photons or matter, they produce pions. Those pions decay into neutrinos. The neutrinos travel across the universe, undeflected by magnetic fields, pointing straight back toward their source. Gamma-ray bursts are another possibility. These are the death screams of massive stars collapsing into black holes or the collisions of neutron stars. For brief moments, they're the brightest events in the universe, releasing in seconds more energy than the sun will produce in its entire lifetime. The physics in those extreme environments can accelerate particles to energies that dwarf anything we can achieve in laboratories. Any system capable of accelerating particles to these energies is operating at the frontier of physics. You're dealing with relativistic shocks, magnetic fields, that would vaporize planets, densities, and temperatures beyond anything we can recreate or even adequately simulate. These are windows into extreme physics laboratories where nature pushes the laws of physics to their limits. Now let's consider a speculative connection, and I emphasize speculative to 3I Atlas. Could an interstellar visitor be embedded in passing through or somehow connected to a high-energy astrophysical environment? The object came from interstellar space. We can calculate its trajectory, trace it back into the galaxy, but we don't know its full history. Did it pass through a supernova remnant? Near a pulsar wind nebula, through regions of space where magnetic fields or plasma densities create particle acceleration zones? If 3I Atlas somehow carries exotic properties fields we don't understand or structure we haven't detected, could it interact with the solar wind or interplanetary medium in ways that produce high-energy particles? Could it through mechanisms that don't operate in normal comets? Seed neutrino production. This sounds absurd until you remember that we don't actually know what 3I Atlas is. We're calling it a comet because it's in our solar system and shows volatile activity, but everything about it is anomalous. If it's not a normal comet, if it has properties or capabilities beyond what natural bodies possess, then all bets are off regarding what it might do or what signatures it might produce. The test is concrete. Neutrino detectors like KM3net IceCube at the South Pole and others maintain continuous monitoring. Their data is time-stamped and direction resolved. You could search these databases for neutrino detections, coincident with 3I Atlas's perihelion passage, active phases, or any unusual behavior observed optically or spectroscopically. The correlation would need to be statistically significant, far beyond what you'd expect from random chance. Given typical neutrino detection rates and the observation windows for Atlas, you can calculate the probability of random coincidence. If you found multiple high-energy neutrino events, all temporally and directionally consistent with originating from Atlas's location, that would be extraordinary. It would immediately elevate the object from weird comet to high-energy astrophysical phenomenon. The precedent exists. When IceCube detected neutrinos from the direction of the blazar TXS 0506+056, during a period when that blazar was in an active flaring state, it confirmed that blazars are indeed neutrino sources. Multi-messenger astronomy, correlating signals across different types of particles and radiation, has proven to be incredibly powerful for understanding cosmic sources. Light neutrinos, gravitational waves. Each messenger tells you something different because each is produced by different physics and travels through space differently. Neutrinos are special because they're so hard to stop. If 3i Atlas were producing them, they'd escape directly, carrying information about whatever process is generating them. Gamma rays might be absorbed by dust or gas. Radio waves might be scattered, but neutrinos punch through everything. The 220 PeVi detection is proof that such messengers are out there, that we're living in a universe with processes violent enough to produce them. It's a reminder that our census of cosmic phenomena is incomplete, that nature operates at energy scales, and through mechanisms we're only beginning to map. So when we look at 3i Atlas with all its contradictions and anomalies, we should keep in mind that the universe has already shown us it can do things we didn't predict. ASCAP J1832 pulses in ways no model fully explains. A neutrino with unimaginable energy came from somewhere. Black holes merge and produce gravitational waves. Fast radio bursts flash from distant galaxies. The inventory of cosmic weirdness keeps growing. Maybe 3i Atlas is just another entry. Maybe it's connected to other phenomena through physics we don't yet understand. Or maybe it's something else entirely, something that will require new categories, new theories, new frameworks. The only way to find out is to keep observing, keep correlating, keep asking whether different anomalies might be linked. And to do that effectively, we need access to all the data, including observations that might be sitting in archives, waiting to be analyzed, or streaming from detectors that haven't yet been searched for the right correlations. The questions are askable. The data exists. What remains is the determination to pursue the answers. While astronomers have been wrestling with 3i Atlas's contradictions, the sun has been making the life difficult for everyone trying to observe anything at all. In mid-October 2025, our star launched 4 coronal mass ejections toward Earth in quick succession. Massive clouds of magnetized plasma traveling through space at millions of kilometers per hour expected to arrive between October 15th and 17th. For aurora watchers, this is exciting. Geomagnetic storms drive charged particles into Earth's upper atmosphere near the poles, where collisions with atmospheric gases produce the shimmering curtains of light we call aurora. The stronger the storm, the farther from the poles, the aurora can be seen, sometimes extending to mid-latitudes, in spectacular displays that thrill photographers and sky gazers. For astronomers trying to observe faint objects, space weather is a nightmare. Here's what happens. A coronal mass ejection, or CME, is an eruption of plasma and magnetic field from the sun's corona. When these billion-ton clouds hit Earth's magnetic field, they compress and distort it, creating a geomagnetic storm. The effects cascade through multiple layers of Earth's environment and can dramatically impact observations. The ionosphere, the layer of Earth's atmosphere between about 60 and 1,000 kilometers altitude that's partially ionized by solar radiation, becomes turbulent during geomagnetic storms. Its density varies, creating regions of varying refractive index. Radio waves passing through this ionized layer get bent, scattered, and delayed by different amounts at different times. This is called ionospheric scintillation, and it's the bane of radio astronomers. Signals from distant radio sources shimmer and fade, like stars twinkling, but worse, making precise measurements difficult or impossible. Cosmic ray showers increase during geomagnetic storms. The same charged particles creating auroras are hitting Earth's atmosphere all around the planet. When these high-energy particles collide with atmospheric molecules, they create cascades of secondary particles that rain down to ground level, detectors. Whether telescopes, particle detectors, or spacecraft instruments get hit with spurious signals, noise that has to be filtered out carefully during data processing. Optical observations suffer from airglow, where excited atmospheric molecules emit light that adds background noise to images. During geomagnetic storms, airglow intensifies, reducing the contrast between faint astronomical sources and the sky background. It's like trying to photograph faint stars at twilight instead of under dark skies, possible but harder. Spacecraft face direct effects. Solar energetic particles, high-energy protons and heavier ions accelerated by the CMEs and by shocks. Traveling through the solar wind can cause bit flips in electronics. A high-energy particle strikes. A memory chip changes the state of a transistor, and suddenly, a 0 becomes a 1 or vice versa. This corrupts data or triggers false readings. Modern spacecraft have error detection and correction systems, but they're not perfect. Star trackers. The cameras that spacecraft use to determine their orientation by photographing star patterns can be confused by high-energy particles hitting their sensors. The particles create false stars, bright spots that appear and disappear frame to frame, making it harder for the spacecraft to figure out which way it's pointed. If attitude determination fails, observations might be missed or pointed incorrectly. Camera sensors themselves show noise during particle storms. Cosmic ray hits appear as bright streaks or spots in images. Most of these can be identified and removed during processing. They're easy to distinguish from real stars because they usually appear in only a single frame, but heavy bombardment can degrade image quality or require longer integration times to accumulate enough signal above the noise. All of this has to be filtered out, corrected, accounted for during data analysis. And sometimes the corrections aren't perfect. Sometimes data is genuinely degraded or lost. Here's where it gets insidious. Space weather creates plausible deniability for data problems. If frames are missing from an archive, if images show unexpected artifacts, if telemetry has gaps, you can always blame space weather. A CME hit during that observation window. Solar energetic particle event corrupted the data. The spacecraft had to safe mode because of the storm. All of these are legitimate effects that really do happen, but they're also convenient excuses. How do you distinguish between genuine space weather impacts and other reasons data might be incomplete or problematic? You look at the details. Space weather effects leave specific signatures. Cosmic ray hits appear as sharp spikes in single pixels or small clusters with characteristic energy deposition patterns. Ionospheric scintillation shows up as time-variable signal strength with frequency dependencies that can be modeled. Spacecraft safe modes generate specific telemetry patterns and log entries documenting why the safe mode was triggered when systems were restored, what data might have been affected. If you have access to the full metadata engineering telemetry event logs, detailed observation reports, you can usually tell what happened. The problem is when you don't have that access. If you're just told data was lost due to space weather, without seeing the detailed logs, the instrument diagnostics, the before and after calibration frames, you can't verify the claim. It might be completely true. It might be a simplification of a more complex situation where space weather was one factor among several. Or it might be covering something else entirely. This isn't paranoia. This is how data integrity works in science. Claims require verifiable evidence. Evidence requires provenance. You need to know where data came from, how it was processed, what happened to it along the way. When gaps appear in that chain of custody, when explanations are vague or incomplete, the data becomes less reliable for making strong claims, whether those claims are mundane or extraordinary. Historical examples show how space weather complicates missions. The Hubble Space Telescope's NICMOS instrument had a cooling system failure initially attributed to generic thermal issues. Investigation revealed specific mechanical problems that took years to fully diagnose. Mars Observer was lost during orbital insertion with telemetry, suggesting a fuel line rupture, but the incomplete data left room for alternative theories that couldn't be definitively ruled out. For 3I Atlas observations specifically, space weather matters because we're relying on a patchwork of instruments, each with different vulnerabilities. Ground telescopes fight atmospheric effects exacerbated by geomagnetic storms. Space telescopes deal with particle radiation. Radio arrays cope with ionospheric scintillation. If these instruments are showing slightly different results, how much is due to genuine physical differences in what they're observing versus instrumental and environmental effects? The 4 CMEs arriving in mid-October 2025 add another layer of complication. Any observations during this window will have larger error bars, more uncertainty, more potential artifacts. This doesn't make the observations worthless, but it does mean we need to be more careful about interpretation, more rigorous about calibration, more conservative about claims. There's also a timing question that's worth noting, even if it doesn't prove anything. If decisive spacecraft observations of 3I Atlas exist, if there are frames that would resolve the contradictions we've been discussing, why haven't they been released during a week when space weather provides a ready-made explanation for any delays or data issues? It would be the perfect time to say, we wanted to release earlier, but the CMEs complicated our data processing. Here's what we have. The absence of such an announcement is noticeable. It doesn't necessarily mean anything. Mission teams have their own schedules and priorities that don't revolve around public speculation, but it's one more data point in the pattern of missing information. Space weather is part of the structural blindness we face when trying to understand cosmic phenomena. The environment between us and the object between the instrument and the data archive between observation and publication introduces noise gaps, uncertainties. Some of this is unavoidable physics, some is technological limitation, and some might be institutional or procedural, the way data gets handled and released by organizations with their own constraints and priorities. To get past this blindness, we need multiple strategies, redundancy, multiple instruments, multiple observations, multiple independent analyses of the same data, transparency, open data policies, clear documentation of processing steps, accessible metadata, and a culture where asking questions about data provenance isn't seen as adversarial, but as essential to doing rigorous science. The space weather will pass, the CMEs will dissipate, conditions will return to normal. And we'll still be left with the question, what is 3I Atlas and why can't we get a straight answer? Enough speculation. Enough grappling with ambiguous data and missing observations. Let's talk about what can actually be done, what experiments would provide decisive answers, what observations would force us to accept one explanation and reject others. These are concrete, achievable tests using existing technology and established observational techniques. Test 1: high-resolution polarimetry at multiple phase angles. Polarization is a property of light that most people never think about, but astronomers rely on constantly. Light is an electromagnetic wave, an oscillating electric and magnetic field propagating through space. Unpolarized light, like sunlight, has its electric field oscillating in random directions, perpendicular to the direction of travel. Polarized light has the oscillations preferentially aligned in one direction. When unpolarized sunlight scatters off particles, the scattered light becomes partially polarized. The degree and direction of polarization depend on the scattering angle, the particle size, composition, and shape. This makes polarimetry, measuring the polarization of light, an extraordinarily powerful diagnostic tool. For 3i Atlas, observing polarization at multiple phase angles would reveal surface and coma properties without ever touching the object. Dust particles scatter sunlight with predictable polarization signatures. Metallic surfaces produce different patterns than fluffy aggregates of ice and organics. Smooth faces polarize differently than rough textures. The phase angle, the angle between the sun object and Earth, matters because scattering behavior changes with geometry. By measuring how polarization varies across different phase angles, we can infer particle properties, surface roughness, compositional gradients, potentially even detecting artificial surfaces if they exist. If the polarization signature matches typical comet dust, that supports natural hypotheses. If it shows patterns consistent with metals, crystalline structures, or geometric surfaces, that's anomalous and demands explanation. The observations require polarimeters on large ground-based telescopes, or possibly HST instruments that exist and are regularly used. Test 2: narrowband imaging. During dormant phases. Most of the intensive observations of 3i Atlas happened near perihelion, when the object was closest to the sun and presumably most active. That's natural objects are brightest when heated by intense solar radiation. But this focus means we've potentially missed crucial evidence about what powers the object's activity. The test is simple: observe Atlas far from the sun using narrowband filters that isolate specific molecular emission lines. These filters, just a few nanometers wide, block out continuum light and reveal only emission from specific molecules: water, carbon monoxide, carbon dioxide. If the object is a normal comet, emission should drop dramatically when it's far from the sun and cold. The relationship between solar distance and activity is well established. Beyond about 3 AU, most water emission ceases. CO persists farther but eventually fades. If gas production continues when solar heating can't sustain it, that requires explanation. Natural processes like stored internal heat or radioactive decay produce some residual warmth, but there are limits. Significant activity beyond 5 AU would be extraordinary, suggesting either exotic composition or an internal energy source beyond what solar heating alone provides. The observation campaign should span multiple points in the orbit tracking when activity starts, peaks, and ends. Any deviations from solar distance-dependent activity curves provide clues about internal structure and energy budgets. Test 3. Deep stacking with adaptive optics or space telescopes. Get the highest resolution images possible. Use adaptive optics on 8 to 10 meter class telescopes, Keck VLT Gemini, to overcome atmospheric blurring and achieve near diffraction limited performance. Request JWST or HST time specifically for imaging, not just spectroscopy. Stack dozens or hundreds of exposures to maximize sensitivity to faint structures. Image at multiple wavelengths to separate dust continuum from gas emission. Create color maps revealing compositional variations. Use difference imaging, subtracting images taken at different times to highlight changes. If 3i Atlas has extended structure, this approach will reveal it. Natural objects have irregularities, brightness variations, asymmetries. Even nominally compact objects show some spatial extent when you push sensitivity far enough. A completely featureless point source would itself be unusual and suggestive. Look for cometary features, jets, fans, shells, and for geometric patterns that shouldn't occur naturally. Resolution requirements are demanding but achievable, resolving structures at scales of tens to hundreds of kilometers on the nucleus. Test 4. Coordinated multi-wavelength monitoring. Organize a campaign involving radio telescopes, X-ray satellites, optical instruments, and ultraviolet observations, all watching 3i Atlas simultaneously during an active period. This requires advanced coordination across facilities and willingness from time allocation committees to support what amounts to a fishing expedition. The goal is catching correlations. If optical brightening coincides with radio pulses that suggests electromagnetic activity, if X-ray flashes align with spectroscopic gas detections that implies specific plasma processes, if everything varies independently that's consistent with chaotic natural activity, but synchronized behavior across unrelated wavelengths would be remarkable. Natural processes typically don't show tight correlations across vastly different energy scales unless there's common triggering or organized energy conversion. The observational cadence matters. Some phenomena happen on minutes to hours timescales, requiring continuous coverage while others unfold over days. Test 5, Neutrino and Cosmic Ray, Coincidence. Monitoring. This test requires luck and cooperation from particle physics collaborations. Petition KM3Net, IceCube, Pierre Auger Observatory and Telescope Array to search their databases for events coincident with 3i Atlas observation windows. The probability of random coincidence is calculable. Given typical detection rates and the observation windows, we can determine how many matches we'd expect by pure chance. A statistically significant excess would be extraordinary, immediately elevating Atlas to high-energy astrophysical phenomenon status. Comets don't emit detectable neutrinos or cosmic rays. If Atlas does, it's operating through physics beyond standard cometary processes. The sensitivity is limited. Unless the object produces substantial flux, we won't detect anything, but the potential payoff justifies the effort, especially since searching existing databases requires minimal new resources. Test 6, Rotation and Light Curve Analysis. All solar system bodies rotate, and their brightness varies as different parts of their surfaces face the sun and observer. Detailed light curve analysis measuring brightness variations over time can reveal rotation periods, axis orientations, sometimes even rough shape models.
If SIR Atlas shows regular periodic variations, the period and amplitude tell us about shape and spin. Short periods suggest small, cohesive bodies. Long periods might indicate large objects or tidal locking to some external influence. Large amplitude variations suggest elongated or irregular shapes. Small variations suggest spherical bodies, or viewing down the rotation axis. If the light curve is unusually stable, too smooth, lacking the irregularities that natural tumbling bodies show, that would be anomalous. Real asteroids and comet nuclei have surface features, bright and dark patches, topographic relief producing light curve irregularities. A perfectly smooth light curve suggests either remarkably uniform surface or active compensation for natural variations. If variations correlate with activity indicators in ways suggesting control rather than passive response, that would be significant.
For instance, if gas emission pulses always occur at specific rotation phases, that suggests deliberately positioned vents. If brightness changes lead or lag rotation phases inconsistently with passive solar heating, that implies active processes modulating output. The observation program requires sustained monitoring over complete rotation periods, which might span hours to days. Automated telescopes and photometric networks can provide continuous coverage with multiple sites, ensuring 24-hour observation. Test 7, Magnetic Field Detection. Via Faraday rotation radio waves, passing through magnetized plasma experience and Faraday rotation, where the polarization angle twists proportional to field strength and plasma density. This effect, predicted by classical electromagnetism and observed throughout astrophysics, provides a direct probe of magnetic fields. If 3i Atlas has magnetic fields and an ionized coma background, radio sources seen through that coma should show rotation.
The geometry requires alignment. Atlas must pass in front of or near bright radio sources as viewed from Earth. These events are rare but predictable using orbital calculations and radio source catalogs. The observation is technically challenging, requiring precise polarization measurements at multiple times to detect changes as Atlas moves relative to background sources. Ionospheric Faraday rotation must be calibrated out since Earth's ionosphere also rotates polarization, but it's achievable with very long baseline interferometry networks. Comets don't have intrinsic magnetic fields. Their nuclei are too small and non-metallic. Any field detection would be extraordinary, suggesting metallic composition, internal dynamos, or electromagnetic systems operating beyond natural processes. Field strength and structure would constrain models of what's generating it. Each test makes specific predictions under different models.
Natural comet with unusual composition expect comet-like polarization activity only when solar-heated irregular shape and rotation, no multi-wavelength correlations, no magnetic fields. Fragment swarm, slightly unusual polarization from collective scattering, extended but compact structure, chaotic light curves, no organized electromagnetic behavior. Electromagnetically active through exotic natural processes, anomalous polarization, magnetic field detection, multi-wavelength correlations, possible activity even far from sun. Artificial all bets off but potentially geometric structures, organized behavior, non-natural spectra, temporal patterns suggesting control. The key is falsifiability. We can state in advance what results would support or contradict each hypothesis. That's how science works. You make predictions, test them, update beliefs based on results. What we can't do is continue with ambiguous observations that can be interpreted multiple ways, depending on prior assumptions. We need observations designed to break ties, force conclusions, eliminate possibilities. That requires coordinated effort, telescope time allocation prioritizing these questions, and willingness from observatories to invest resources in what might seem like long-shot investigation. But the scientific payoff is enormous. Either we confirm Atlas is a weird comet and learn something new about cometary physics, or we discover it's something else entirely, and open a new field of study. The observation windows are coming. Atlas will have future perihelion passages, future active phases, future opportunities. The question is whether we'll seize them or whether Atlas will remain an ambiguous footnote in the catalog of interstellar visitors. Let's step back and ask the larger question.
What does all this mean? Not just for understanding one unusual object, but for how we do science, how we handle anomalies, how we prepare for discoveries that might challenge our fundamental assumptions about the universe. We're standing at a peculiar threshold in human history. For the first time, we have instruments sensitive enough and surveys comprehensive enough to detect interstellar visitors passing through our solar system. Before the last decade, such objects could have come and gone without us ever noticing unless they happened to become bright, naked-eye comets, and even then we wouldn't have recognized them as interstellar without detailed orbital calculations. Now we see them. One are Oumuamua in 2017, bizarre in its own right with its elongated shape and unexplained non-gravitational acceleration. 2I Borisov in 2019, which looked like a normal comet and behaved like one providing a comforting moment of, see, most of them are just comets. Thunder, and now 3I Atlas breaking the rules, again refusing to fit the categories. Statistical models suggest dozens of interstellar objects pass through the inner solar system every year. Most are too faint to detect. The Vera Rubin Observatory, when it reaches full operation, will find them by the hundreds. Each one is a messenger from another star system carrying information about formation conditions, compositions, and processes in environments we can't visit directly. Each one is an opportunity to test our assumptions and possibly discover we were wrong about things we thought we understood. But here's the uncomfortable reality: we're not prepared for what we might find. Not technologically, our instruments are advancing rapidly. Not scientifically, we can develop new models as needed. We're unprepared institutionally and culturally.
We don't have robust frameworks for handling discoveries that challenge fundamental assumptions. We don't have clear protocols for data transparency when observations are anomalous. We don't have procedures for international coordination when something potentially significant is detected. Consider what happens if 3i Atlas or some future interstellar visitor shows unambiguous evidence of artificial origin. Not ambiguous anomalies open to interpretation, but definitive signatures that no natural process could produce. Geometric structures visible in high-resolution images. Spectral lines from technetium or other elements that only exist as products of technology. Radio emissions with structure suggesting modulation rather than natural chaos. Behavior that adapts to environmental conditions in ways suggesting responsiveness rather than passive reaction. Who decides when evidence crosses the threshold from interesting anomaly to confirmed artifact? Who makes the announcement? How do you prevent premature claims that damage scientific credibility while also avoiding suppression of legitimate discoveries? What happens to the data? Does it remain in restricted archives, or is it immediately released for independent verification? The International Academy of Astronautics has SETI protocols, guidelines for how to handle detection of artificial signals. They emphasize verification, international notification, and coordination before public announcement. But these are voluntary guidelines, not enforceable regulations. And they were written assuming radio signals, not physical artifacts. The procedures for handling a detected spacecraft or probe from another civilization simply don't exist in actionable, internationally agreed-upon form. There are parallels in history, though none quite capture the full scope.
The discovery of nuclear fission required international coordination and eventually led to non-proliferation treaties and monitoring regimes. The development of biotechnology prompted discussions about safety protocols and ethical boundaries. Climate science has struggled with the challenge of communicating findings with enormous implications while facing organized opposition and institutional inertia. But discovering evidence of extraterrestrial intelligence, finding artifacts from another civilization, would be different in kind, not just degree. It would immediately raise questions about communication intentions, potential risks, and appropriate responses. And those questions would need to be addressed by institutions, space agencies, governments, international bodies that haven't prepared for them. Even if 3i Atlas turns out to be natural, the fact that we're having this conversation, that the observations are strange enough to warrant considering exotic possibilities, reveals our lack of preparedness. If not this object, then eventually some future observation will push us into uncomfortable territory where standard explanations fail, and we're forced to consider alternatives we'd rather not contemplate. Are we in a strangeness era of astronomy? The evidence suggests yes. Fast radio bursts weren't discovered until 2007, not because they're rare, but because we weren't looking in the right way. Now we detect dozens daily and still don't fully understand their origins. Gravitational waves from black hole mergers were theoretical until LIGO detected them in 2015, opening an entirely new observational window. ASCAP J1832 pulses every 44 minutes in patterns no model adequately explains. A 220 PeV neutrino points to particle acceleration we can't fully account for. The common thread is that new instruments reveal new phenomena. We're finally looking at the universe with sufficient sensitivity temporal coverage and multi-wavelength capability to see its full complexity. And that complexity includes objects and events that don't fit our existing categories. Some will be explained by extensions of known physics. Some might require new physics, and some rarely, perhaps, vanishingly rarely, but not impossibly, might be technological. The philosophical question underneath everything is whether we're manufacturing mysteries through observer bias or revealing genuine strangeness. I lean toward the latter.
The universe is under no obligation to conform to human intuition or models developed from a tiny sample of phenomena accessible to 19th and 20th century technology. Quantum mechanics is strange. Relativity is strange. Dark matter and dark energy constitute 95% of the universe's mass energy budget, and we have no idea what they actually are. Each generation discovers that reality operates on principles that seem bizarre until you understand them, and often remain bizarre even after understanding. So maybe we should expect interstellar visitors to be weird. Maybe we should expect phenomena at the edges of observational capability to challenge our models. Maybe the appropriate response to 3i Atlas isn't to force-fit it into categories that don't quite work, but to acknowledge uncertainty, pursue rigorous investigation, and be prepared for answers that surprise us. The choice we face is clear. We can continue with scattered, uncoordinated observations that leave ambiguities unresolved. We can accept incomplete data and vague explanations. We can prioritize institutional convenience over scientific rigor. Or we can mount a focused campaign designed to get decisive answers, demand transparency in data handling, develop protocols for handling discoveries that challenge assumptions, and commit to following evidence wherever it leads. The infrastructure for the second path exists. The telescopes operate. The archives are maintained. The procedures for data requests and scientific coordination are established. What's lacking is, will the collective determination to prioritize these questions, invest the resources, navigate the bureaucracy, and maintain pressure on institutions to provide transparency. This isn't just about 3i Atlas. It's about how we do science when confronting genuine anomalies. It's about maintaining intellectual honesty while remaining rigorously skeptical. It's about building systems that can handle discoveries we haven't anticipated. It's about being ready for the universe to surprise us. Because one thing history has taught us, the universe always has more surprises. The frontier keeps expanding, and somewhere in the data we haven't fully analyzed, in observations we haven't made, yet in patterns we haven't recognized, the next profound discovery is waiting. The question is whether we'll find it. What we know, what we need, and what happens next. Let's bring this back to solid ground. Let's separate what we actually know from what we're speculating about, and let's define clearly what needs to happen next. What we know with high confidence. Tests stacked over 9,000 frames of 3i Atlas and found no extended coma, observing it as a point source. This observation is reproducible, documented, and released in peer-reviewed format. JWST and SphereX detected gas emissions, water vapor, and carbon dioxide, indicating volatile activity. These spectroscopic observations are solid based on well-understood molecular physics. Ground-based optical telescopes reported varied results, with some seeing slight asymmetries and others seeing minimal structure. The observations are real but inconsistent across instruments and time. The object's interstellar origin is confirmed through orbital calculations showing hyperbolic trajectory. It came from outside our solar system and, unless captured, will eventually leave. Its basic physical parameters, approximate size, brightness, distance, are measured and tracked continuously by multiple observatories. What remains ambiguous? The physical mechanism producing gas without proportional dusttail, whether electromagnetic or plasma effects play any unusual role. Whether the contradictions between instruments reflect genuinely anomalous behavior or primarily observational selection effects, timing, mismatches, and instrumental differences. The detailed composition and internal structure of the nucleus. Whether any potential spacecraft observations exist, and if so, their quality and accessibility. What is pure speculation? That 3i Atlas might be artificial or technological. That spacecraft data is being withheld for non-scientific reasons. That there's a pattern connecting different cosmic anomalies through shared exotic physics. These are hypotheses worth exploring and testing, but they're not supported by conclusive evidence. They represent possibilities to investigate, not facts to accept. The verdict ladder. How do we move from weird comet to exotic natural phenomenon to possibly artificial? The path requires accumulating multiple independent lines of evidence, each pushing us further from standard explanations. Natural explanation remains the default, requiring only that we find some plausible combination of composition structure and environmental conditions, explaining observations without invoking new physics. Most scientific anomalies resolve here. Unusual but natural parameters, edge cases in known distributions rare but possible configurations. Exotic natural explanation requires identifying processes operating in 3I Atlas that don't occur in typical comets but remain consistent with known physics. Perhaps electromagnetic effects confining dust, crystalline ice structures changing sublimation dynamics, or fragment swarms with collective behavior. This represents expansion of comet taxonomy rather than abandonment of natural categories. Artificial explanation requires multiple independent lines of evidence showing behavior inconsistent with any natural process. Geometric structures indicating design, spectral signatures from industrial materials, temporal patterns suggesting control energy budgets exceeding what passive solar heating provides. The bar is appropriately high. Extraordinary claims require extraordinary evidence. The critical path. 3. Decisive investigations. First, archival forensic recovery.
Access Psyche spacecraft data or any other spacecraft observations during Atlas encounter windows. Verify whether images exist, examine them for structure, and morphology, authenticate metadata and processing history. This is the most direct test because high-resolution spacecraft images would definitively show the object's appearance. Technical barriers are low. The data, if it exists, is stored somewhere. Accessing it requires navigating institutional procedures, filing formal requests, potentially using FOIA processes. Bureaucratic friction is the main obstacle, not technical capability. Second, decisive multi-wavelength coordinated observation. Organize a campaign during Atlas's next active period with polarimetry, spectroscopy, radio observations, X-ray monitoring, and particle detector correlation. This comprehensive approach captures phenomena that single instrument observations miss. It tests whether Atlas shows electromagnetic activity, whether behavior is periodic or chaotic, whether it produces any signatures beyond standard cometary emissions. Success requires coordination across facilities' advanced planning and telescope time allocation. The observations are technically feasible with existing instruments. What's needed is prioritization and resource commitment. Third, high-energy event correlation. Continuously monitor neutrino detectors, cosmic ray networks, and gamma-ray observatories for statistically significant correlations with Atlas activity. This tests the most extreme hypothesis connection to high-energy astrophysical processes. It's a long shot, but the data exists in real-time streams that can be searched retrospectively. If correlation appears, it transforms understanding of the object. If correlation is absent, it eliminates a category of exotic explanations. Either outcome advances knowledge.
The 90-day action plan. Days 130 Organized Citizen Audit Coalition. Divide archival search tasks among volunteers with appropriate skills. File FOIA requests for Psyche data and mission logs. Begin systematic downloading and reprocessing of available images from all missions that might have observed Atlas. Develop tools for automated archive searching and metadata analysis. Days 30-60. Compile results from archival searches. Identify gaps, anomalies, mislabeled data. Prepare telescope proposals for coordinated observation campaign during next Atlas active period. Reach out to neutrino detector collaborations requesting correlation analysis. Begin public advocacy campaign for data transparency through science communication channels. Days 60-90. Submit observation proposals to time allocation committees. Follow up on FOIA responses escalating through appeals, process if necessary. Publish preliminary findings from archival analysis in open access formats.
Establish communication channels with professional astronomers willing to contribute expertise and telescope time. Create public dashboard tracking investigation progress, how you can contribute. If you have data science skills, volunteer to help search archives and develop analysis tools. Python knowledge of astronomical databases and experience with large dataset processing are valuable. If you have access to telescopes, even small amateur instruments, contribute observations during coordinated campaigns. Time series photometry, basic imaging, and spectrum collection from distributed observers provide valuable data density. If you have legal expertise, assist with FOIA processes and data access requests. Understanding how to navigate government transparency mechanisms accelerates archive access. If you have platforms or audiences, raise awareness and apply pressure on institutions for transparency. Public interest influences institutional priorities more effectively than internal advocacy alone. If you have funding capacity, consider supporting citizen science efforts through grants or crowdfunding. Even modest resources dramatically accelerate analysis capacity, enable conference attendance for coordination, and support development of open-source tools. The emotional core. We're standing at a threshold. We have an object behaving strangely enough to demand explanation technology capable of providing that explanation and a choice about whether to pursue it rigorously or accept comfortable ambiguity. The easy path is calling it a weird comet and moving on. Ambiguity is comfortable. It doesn't require difficult observations, bureaucratic battles, or intellectual risk. The harder path is acknowledging we don't understand it yet and committing to finding out why. That requires resources, persistence, and courage to pursue conclusions wherever evidence leads. Science progresses through exactly this kind of moment. When observations don't fit, when standard models creak under anomalies' weight, you must decide whether to patch with ad hoc explanations or consider that something fundamental might need revision. Most of the time, patches work and standard models survive, refined and strengthened. But occasionally, rarely, anomalies signal something deeper, requiring fundamental rethinking. We don't yet know which kind of moment this is. 3I Atlas might be a comet with unusual but ultimately explicable properties, or it might be the first clear example of something uncategorized, natural but exotic. Or, in the scenario that sounds like fiction but can't be dismissed without evidence, it might be the first detected artifact from beyond our solar system. The probability of that last option is low, but low is not zero, and implications are too significant to ignore just because they're uncomfortable. What we know definitively is the mystery is open. Tools are available. Tests are defined. We don't yet have proof of the impossible, but we have the strongest clues yet about something not fitting our understanding. The data exists somewhere in archives, in instruments pointing skyward right now, in databases waiting for correlation analysis. The question is whether we have collective will to pursue it, rigor to do it properly, and courage to accept whatever answers emerge. This is how discovery happens. Not through sudden revelation, but through accumulated anomalies, forcing questions, investigations, following those questions wherever they lead, and communities collaborating to turn observations into understanding. The 3I Atlas mystery invites us into that process, offers a role in figuring out what's real versus misinterpretation. So let's test it. Demand the data, perform the observations, do the analysis. See what the universe actually tells us. Because the only thing worse than discovering we're wrong about something fundamental would be having the opportunity to discover that and choosing not to look.
The frontier is open. Right now, as you listen to this, 3i Atlas is moving through our solar system carrying secrets we haven't fully unraveled. Right now, data that could answer our questions might be sitting in archives stored on hard drives in server farms, waiting for someone with determination to find it. Right now, telescopes are tracking the night sky, capable of making the observations that would resolve the contradictions. We've journeyed through the evidence tonight. We've examined how TESS sees a point source, while JWST sees vigorous gas emission. We've explored why different instruments paint incompatible pictures of the same object. We've considered natural explanations requiring unusual conditions, exotic natural explanations requiring physics. We haven't observed at these scales, and yes, the uncomfortable possibility that we might be looking at something artificial. We've talked about missing spacecraft observations that could settle everything, about bureaucratic obstacles to data access, about space weather providing convenient excuses for gaps and delays, about the experimental tests that would force conclusions rather than perpetuating ambiguity. And we've placed all of this in cosmic context. ASCAP J1832 pulsing every 44 minutes in defiance of models, a 220 PeV neutrino pointing to extreme physics, a universe constantly surprising us with phenomena we didn't predict. The verdict isn't in yet. Science doesn't work on schedules aligned with documentary narratives. The truth emerges through painstaking observation, careful analysis, rigorous testing. It might take months, it might take years, but the questions are now clearly formulated. The tests are defined. The path forward is visible. What happens next depends on choices. Institutional choices about data transparency and observation priorities. Individual choices about whether to engage with the mystery, contribute skills, demand accountability. Collective choices about whether we value the comfort of ambiguity or the difficult pursuit of truth. 3i Atlas won't be the last interstellar visitor. More are coming. The Vera Rubin Observatory will find dozens, eventually hundreds. Each one is another test of our understanding, another opportunity to discover whether our models are complete or whether the universe has more surprises waiting. And perhaps the deeper question, the one that lingers after all the technical details and scientific arguments have been laid out, is this: if we can't handle ambiguity around one unusual comet, if we can't maintain both rigorous skepticism and genuine openness to unexpected possibilities, if we can't build the institutional frameworks and cultural readiness for discoveries that challenge assumptions, then what happens when we encounter something that can't be explained away? What happens when the evidence becomes unambiguous? Are we ready for the universe to show us that we're not alone? Are we prepared for the possibility that some of the messengers arriving from the stars might carry messages we didn't expect? The answer to those questions won't be determined by what 3i Atlas turns out to be. It will be determined by how we respond to the mystery it presents, by whether we choose rigorous investigation or comfortable ambiguity, by whether we demand transparency or accept opacity, by whether we follow the evidence or retreat into the familiar. The cosmos doesn't care whether we're ready. It will keep sending visitors, producing phenomena challenging our comfortable certainties. The only question is whether we'll be watching when the truly profound discovery arrives and whether we'll recognize it for what it is. So keep looking up, stay curious, demand answers, and remember that the greatest discoveries often hide in the anomalies we're tempted to dismiss, in the observations that don't quite fit, in the mysteries we almost ignored because they made us uncomfortable. Somewhere in the darkness between the stars, 3i Atlas continues its journey, carrying its secrets. And somewhere in the data archived streaming, waiting to be collected, the truth is waiting for us to find it. The question isn't whether the truth exists, it's whether we'll do the work to uncover it. Sweet dreams, and may your curiosity outlast the darkness.